I'm going to show to you this slide at least 4 other times during this course. A couple of times today, and from a totally different perspective on Friday, when hopefully we're going to speak about surface waves. Now, this slide here is containing a very simple idea, just pure geometry. Now we have a surface here, okay? This one. It's for example, the free surface, where, for example, we have a set of receivers. So, starting from your question, we can imagine now to have a set of receivers. Maybe we are the receivers, and we're sitting on a free surface. Something is coming from downstairs. We don't know the direction. But what we can do is to imagine to have clocks with us, to have positions, like a GPS, and we can measure the velocity of a perturbation between us. Now, there are two extreme situations. The first one, let's imagine that K is totally Kz. Now, you can imagine that if a P is coming, we're going to jump together, because it's arriving at the same time at our different positions. Okay, now let's call the velocity of this information as horizontal apparent velocity. It's horizontal because we are sitting on horizontal free surface, okay? It's apparent because we don't see the real velocity, but we are measuring the horizontal apparent one. Now, if we are jumping together in phase, what is the velocity? It takes no time for information to travel between us. That's infinite. We are jumping together. In the other case, let's imagine that the wave is not kz, is kx, and it is arriving. I'm moving, then you're moving, then you're moving. If we take the clocks, velocity will be wave velocity. Is it okay up to now? So, we don't know the real k, but we can measure kx. That is omega over what we measure. Is it okay? Let's give a look. That's k. Okay? That's the real k, whose direction is telling us where the wavefront is going. Its absolute value could be omega over alpha if it is a p wave, or omega over beta if it is an s wave, okay? Now, this angle, this vector, is creating an angle with this z-axis, right? And so, also an angle with the free surface. And if you give a look, this angle corresponds to the incidence angle. That by geometry is also the angle between the wavefront and the free surface. Pure geometry. Okay? Now, let's imagine this situation. Now, K is totally Kz. Kx is 0. Do you agree with me? Okay. So you have to imagine that when this wavefront is arriving, we are moving together. And it takes no time for information to travel between me and you. That means that the horizontal apparent velocity is infinite. It's not a real velocity. It's a projected velocity. Okay? Now, the name given to apparent velocity is, in this slide here, Cx. It's coming from your textbook, so you can relax. Good. And this situation corresponds to the case when k is totally kz and kx is 0. Now, what is kx? Well, kx is omega over Cx. That is the horizontal apparent velocity. It's just the projection. In this extreme case here, you can imagine that it is 0. Why? Because Cx is infinite. Let's give a look to the other extreme case. The wave is arriving from a specific direction and k is totally kx. Now, omega over Cx is equal to omega over the velocity, alpha or beta. Okay? What about the intermediate situation? Well, it will depend on the angle. When I is 0, this is infinite. When I is 90, this is exactly the wave velocity. What in the middle? Well, we have to work out a very simple trigonometric expression. And now we are going to give some names. The names that we are going to give now will be very important for body waves today. But the same names will be important on Friday for surface waves, and they will have a different meaning. Let's give a look to the top right panel, cartoon. Okay, we have a real K now that is going into some direction. It's making an angle I with the normal, but it is also the angle created by the wavefront with the free surface. Okay, it's just exactly this. Let's decompose K into Kx and Kz. Easy. Well, if you know that angle, that's easy, right? Kx will be K sine of I. Kz will be K cosine of I, right? Good. What about Kx? Well, Kx can be called, is called, this is Kx, as omega over alpha, if it is a P wave, times sine of I. Right? That's in general. When I is going to 0, this is going to infinite. 1 over. When I is 90, this is 1, and this would be alpha. There are no tricks here, just pure geometry. So now we can call it's a name. It's nothing else. It's just pure geometry. You see, when I is going to 0, this is going to infinite. When I is going to 90, this is alpha. Okay? Good. Now, Kx can be also called omega times P. What is P? Well, this. It's a name. Right? What about Kz? Well, Kz is omega over alpha times cosine of E. Okay, let's call this eta. It's a name. Now, those two quantities together represent a vector. P and theta are representing a vector going in the same direction of k with units of 1 over velocity. It's called slowness. That's why S is here. It's the reciprocal of velocity. Now, since you did your homework, can you tell me something about this? That's the quantity related to Snell's law. Do you agree? Yes. So whatever that ray is going to do in its life, that quantity will be constant. You can imagine now to put whatever interfaces, but once the ray starts, the x component of k will be always the same. Z will change to reflect the change of directions, but not x. That's why that P that you see there will become in a few slides what is called ray parameter. It's going to be constant. Once it starts, it's forever. And what does it mean? That the horizontal phase, sorry, that's a lapsus. Horizontal apparent velocity, it will become phase velocity, this one, but in the next lecture. Whatever it's going to do, the horizontal apparent velocity that you measure will be always the same. Okay, up to now we have just given names to very simple quantities. But we have seen that the x component is important because this quantity here is going to stay constant. Whatever is going to happen downstairs. Is it okay up to now? Okay, now it's time to put these names into action. Because now we can write the k's in many different ways. Okay, what about kx? It will be omega times p, full stop. What about kz? It will be omega times eta. Wait a second, we can write it into a different way. Because, for example, we can write the cosine in terms of sine. And we can put together this quantity with this one. Now you take alpha, you take out p, that is, and this is kx, and the relation between kz and kx is contained into this expression here, that is a pure number, and it is called R alpha. It's a name. So, what we have been doing up to now was give a different name to kx and to call kz according to kx. The angles are squeezed here in this ratio. Because if c is infinite, we know that it is totally kz. Okay? If c is equal to a, to alpha, we know that it is 90. So the angle actually is contained into this ratio. There are no tricks here, just giving different names. You can understand why proliferating these names, because this will be very useful. And since kx is a quantity that will be remaining constant, actually, in the other slides, kx is so important that actually we will drop the x, and we will call it small k. And kz will be called, in terms of k, using this R alpha. If you have beta, it's the same. But please just remember that this is nothing else than geometry. Is it okay up to now? Okay, now you can see many ways to write potentials, for example. Classical, with p and theta, collecting omega over alpha with direction cosines, or this one. We're going to use this one. They're all representing the same expression with different names. But please remember this slide, because it's going to appear at least other 2 times. Okay? I've changed a little bit the next slide compared to the version that you have online, because I was thinking that it's clearer. Maybe. Let's see. It's nothing else than a rewriting what was, if you have printed this lecture, you will see just a little bit different names. Okay. By the way, what should we do now? Okay, we want to solve the problem of a P wave that is arriving at a free surface and to understand something about the reflections. Let's write our guess, as we did with the string. Let's apply the boundary conditions. Let's see what's coming out. Okay, what do we have on the top? We have a P wave here. And we are guessing that there is a reflected P and a reflected SP. Why? Because they are working on the same components. It's a guess. If our guess is wrong, the boundary conditions will tell us, no, no, there is no S reflected. Okay? So here we have the incoming P. And now I'm writing it in terms of Kx, Kz, I hope that I was not making mistakes, and this is horizontal apparent velocity. K is omega over c. Okay? That's an S reflected, this is a P reflected, and this is an S reflected. It's our guess. Maybe it's not working. And this will be 0. And A will be equal to A0. Who knows? Okay, this is, I was putting this because there are many ways to write these angles, but it's just geometry. This is the incident angle, reflected angle for P, reflected angle for SB. So that's why it's messy here, but it's nothing else than our guess. What is important here is this. Now we have to apply the boundary conditions. What are the boundary conditions? Okay, all the components that have a Z inside of a stress have to be 0. Now for this problem, we don't care about sigma zy because it's not entering into this game. It's entering into the SH game, but not here. So the two conditions are that sigma z and zz here, they have to be always 0. Now, we have the potentials for displacement. We should insert them in the expressions for displacements. We should compute strains. We should compute stresses. I'm lazy. If you do that, what you get is this. These are the generalization of the problem of a string. Now let's remember something about the string. Let's imagine we have a string, we have an end. Okay, this will be a fixed end. You can imagine a free end. All the energy that is incoming is reflected. Now the problem is more complicated because we see here that actually all the energy is reflected, but part of it will be a P, part of it will be an SP. So it's not 0. Now tell me one thing, and this will be your unofficial homework of 1 minute. What are the angles here? What is Snell's law? Oh. Please do remember. Yes, because remember that R alpha is containing this. It's telling to you the life of Kz given Kx. And in some way, it's the angle. So once you fix the elastic parameters of this half space, and you decide alpha and beta, they are given. It's fixed. So inside R alpha and R beta, this number is fixed. So according to the incidence angle, you will get in R alpha and R beta Snell's law. But we did something more, because now we know also the amplitudes. So we have the angles inside the R's and the amplitudes. Your real homework, since you answered what are the angles, R's, is, and the answer is in your textbook. So it takes 1 minute if you look at that page. Less than 1 minute. What's happening at a normal incidence? Here we have a problem. Because normal incidence, we have infinite values. Because I was not writing here. In normal incidence, the R's are infinite. But there is a different way to write this expression, not using R's, but etas and P's. And P, when you have normal incidence, is going to 0. So you could see, solving your homework, just looking at your textbook at a specific page in a specific place, but for normal incidence, if you have a P that is going like that, it will be totally reflected into a P and no SV. Now, what should we do? We should solve this problem for all the possibilities. What if we have an SV incoming? What we should do was to write this expression using a S incoming, an S reflected, and a possibly, a P reflected. Yes, it's working. What about SH? I was telling you that I was taking shortcuts, so let's just use logic here. Let's imagine that we want to solve that problem with an SH. SH, what does it mean? We have just UI component. Here we have UX and UZ. Please remember this. UI contains only SH. Well, you can add all the possible reflections that you want, but the boundary condition would be that sigma zy is 0, and that is going to give just an SH reflected. Full stop. No other possibilities. So, let me tell you, for a free surface, since we solved P as V, we can easily solve SV, SV, P, and SH, SH. The logic is always the same. Let's write a guess, a good guess. Let's use the boundary conditions to solve the problem. The full boundary conditions will always give us Snell's law as a kinematic condition and amplitudes in terms of dynamic conditions. Everything can be solved using this slide here. So please remember what is here. Just renaming things. And the real important thing here is that the X component is containing something that, as we know from Snell's law, it's going to be constant. But that's why it's important. Cosine will take care about the angles. X is given, and according to the value of kz, we know the direction of k. Is it 0? Okay, everything is kx. Is kx 0? Okay, kz is everything. So please remember that the angles are in the ratio between Cx, Ce, and velocity. Okay, since we solved this applying the boundary conditions, now we can take care about other possibilities. What is funny? Well, it's not so funny, but we should now solve all the possibilities. We considered the free surface. Now we should consider an interface between two different media, like the string. You remember? Thin and thick. Continuity of displacement and of force, now we have stress. Okay, we will discuss together just the simplest case. Which one? SH at a solid interface. Oh, just one word. What if the SH is incoming and we have a fluid on the top? Nothing. It's like a free surface. S cannot go there. Okay? So it's not important. What if we have a fluid and a P wave? P, SB, P. Because P waves are sound. So when they touch a fluid, they are sound waves. They can exist there. Okay? There is a slide later. Now what we have to do, and I'm sure that you are very happy, is to generalize the string problem. Why we are going to discuss this case here? Because it's the most similar to the string, to the heterogeneous string that we discussed a few lectures ago. Okay, now, and these slides are coming from your textbook, so everything is there. Now we have two materials here, as you know. Beta, that is an expression of density and rigidity, 1. Second, beta 2, that is an expression as the square root of rigidity, modulus, and density. Okay? Now we have an incident wave, like at the time of a string, with a given amplitude. What's going to happen here? Well, since we know that SH is communicating also with itself, we are going to guess a reflected and a transmitted. Okay? So, incident, reflected, please give a look. It's this one, minus, plus. It's going up. And the reflected, minus, minus. Please notice that this is beta 2 and beta 1. Because the second one is going to be propagated into a different medium. The R betas contain the angles. Okay? What should we do? Well, we have to do exactly what we did at the time of a string. Now the wavefront is incoming, your homework. It's going to be reflected, it's going to be transmitted. With some angles, with some amplitudes. What should occur at any time on the surface? Well, displacement has to be continuous. We don't want to break the system. Stresses have to be continuous exactly in the same way as we did for the string. Now, the first condition is, okay, the y component of displacement, remember, it's an SH. So the wave is arriving here with a given k, but the displacement is in y, okay? Now, along this axis here, x, for z equals 0, at any time t, they have to be the same. Well, nice. We can write this one, and we're getting the first equation into unknowns. Very good. The second one, stress. But we are lucky, because we have to take care just about one. Sigma z, y. It's the only one that is working with SH waves. That's why I love SH. You know why? Because the algebra is always half. Okay, and you will see this also for surface waves. Second one. Now we have to compute sigma yz. Please remember it's symmetric. So we have to compute 2 times mu times the strain. And the strain is this. But uz is not entering into this game. We have just uy. So there it is. Now we have to remember that mu is different on top and on the bottom. So the two expressions that have to be equal here, now you have to take the derivative with respect to z. This is getting down K's. Of course. So Kx R beta, Kx R beta 2. mu1, mu2. And this here has to be valid for all the x's and for all the times. Now we are getting the second equation in two unknowns. Let's put them together and to look for the amplitudes. This is the transmission coefficient and this is the reflection coefficient. Well, if the two media are the same, what's going to happen? This is going to be 0, this is going to be 1. It's passing with no change. Now let me ask you, what are the angles here? They should include also Snell's law. The reflected one will have the same angle, but the refracted one, the angle could be larger or smaller. Where are the angles here? In the R betas. Please do remember that R beta is a pure number that actually is a ratio giving us an angle. Because it's always the ratio between horizontal apparent velocity and the wave velocity, in this case beta. And actually, if you rewrite it with the definition of the R betas, put in the angles, you get this one. And now you have the angles. And you can imagine what's going to happen in some specific cases. Free surface, T is 0, R is 1. Everything is reflected. Core mantle boundary, we will see. It's an interface with a fluid. No S, it's a free surface. Everything is reflected. Vertical incidence, well, the two angles are 0. Now, look here. These are the impedance contrasts that we studied at the time of the string. So you see, in normal incidence, everything is behaving like a string with two personalities, alpha and beta. But when you move from normal incidence, you have always to remember that SH is reflecting and transmitting an SH, but P and SV, SV, SV and P. Angles are decided by Snell law, but amplitudes are decided by full dynamic conditions, as we did. Okay? So the string that we studied was a very particular case of normal incidence. But you see that the expressions are the same. These ones are more general because they're containing the angles, Snell's law. Time of a string, we didn't need it. There are no angles. Impedance contrasts will decide the angles and the amount of energy transmitted and reflected. Now, what should we do? Well, we should prepare plots like this for all the possibilities. But I'm lazy. So what we do see here is the only one that we're going to study in a full detail. Now, this is the first case of a model that is very near to the Earth reality. This plot here is showing energies and energy fluxes, as we did at the time of the string. Energy is related to the square of amplitude. Flux is related to the time derivative, power, and flux, and an area. And if you remember, energy every time is conserved. Now let's give a look to this plot here. It's the only one that we're going to admire into details. The other ones can be derived in a similar fashion, but we will just use logic, okay? Let's give a look to the numbers here. Now we have two media with different velocities and different densities. These values here are typically representative of the crust over mantle boundary. let's give a look to the numbers. 3.9, 4.6. Well, it's a huge number and quite an important discontinuity. Okay? Yes, on average. This is an average vision. Crust, thickness, and properties can vary in a beautiful way, from continental margins to oceanic margins. But this is a sort of an average. Now, what do we see here? Well, we have some lines. Some lines are referring to the coefficient of transmission and reflection, and the other one is the energy ratio. Now, wait a second, because this is important. Let's give a look to, for example, transmission coefficient. What's going to happen there? Well, it's going to increase and to have a sort of an asymptote there. What about this one? Well, it's going to increase and to have an asymptote there. Now, if we sum the energies, if we compute the energies of reflection and transmission over a unit, what you get here is this and this. What's going to happen? What's happening at 60 degrees? That's the incidence angle. So you take 90, you increase 60. Wait a second, Snell's law. Now the second angle actually is becoming 90. From that point on, all the energy is traveling at the interface. So actually there is pretty much no transmission. We have a sort of total reflection. Why? Because the speed is increasing. So we have a deflection, and then it's going to continue on the interface. Please do remember this, because this number is going to play some tricks. Everything is there. Because you can imagine that now Cx has become everything. Okay? But. Okay. That's one vision, and it's a vision of a realistic model of a transition between the crust and the mantle. What should we do? We should generalize this one to all the possible interfaces. But first, with this example, let's consider a sort of a final specific case that will be very important for surface waves. Still, for today, we will not speak about surface waves, so you can relax. Just wavefronts, different phases that will be reflected and transmitted, but no surface waves. Just wavefronts and rays of what we can call seismic body phases. Now let's give a look to what's happening here. We have something that is coming from the medium number 1, making an angle with the normal. Okay? You can imagine the wavefront from normal, tilting, 60. So it's incoming like that. Now, from 60 on, what's going to be transmitted as a refraction angle that has become 90. What does it mean? Well, Snell's law. Now, this one is 90, so it's beta 2. It's traveling on the interface with beta 2. Now, what's happening here? For angles larger than 60, because you can increase now, it's not forbidden to take 60 and then continue. What's going to happen? That one is still to be beta 2. But now I'm asking to your fantasy to imagine angles that are complex numbers. It's a trick, but it's like if they are complex numbers. Because now remember that refraction angle is 90. But if you go beyond 60 degrees, it's getting a phase. So it has a real value 90 plus something. That something is a phase. And you can see it here. because now Cx is getting really strange. Because horizontal apparent velocity for this will become less than beta 2. And this will become imaginary. Now if C is less than alpha, remember we started from C infinite, then alpha, right? Okay, from infinite to alpha, we have one behavior, and this is real. Right? What if C is less than alpha? Oh, well, it will become imaginary. So if you want, you have a complex angle. What if, now remember homework number 1. What about localized phonons? Do you remember? What's going to happen in the forbidden zone? I hope you answered that. Attenuation in the sense that the kx that was representing propagation along x was damped into minus something real x. And this is what's going to happen there. Because energy cannot travel downstairs, so it's staying here, and the z component is going to be damped and damped. All the energy is going to stay at the interface. That's critical reflection. Come on, guys, you studied it. Right? I remember 2 lectures ago that you told, okay, what's going to happen if we get angles larger than the critical one? Well, the energy is trapped more and more at the interface. So, in the z direction, is not able to propagate. It's damped more and more. You can call it critical reflection. It's like if the angle is getting a 90 degrees plus an imaginary term that is putting some phase in the wave train. So what's to happen here is exactly this. The kz component is becoming exponential. Real. Minus. So it's dead. Cannot penetrate. This concept will give rise to the idea of surface waves in the next lecture, but not for today. So here we can speak just about critical reflection. And what's going to happen? It's not moving. Okay. But actually, the reflection coefficient is becoming a complex number. It has 1 as an amplitude plus a phase. It has to be 1. All the energy now is not going down. But if you move for incident angles that are larger and larger, you see that the wave train is changing because now it has a phase. You're changing the phase of the signal, not the amplitude. Okay. So actually, it's just a different way to give a look to what you called critical reflection in optics, I think. Here it's more complicated. Sorry for you. Now what should we do? This. And this is the most complicated interface. Why? Because we should bookkeeping all the possible reflection and transmissions. Because at a solid-solid interface, a P can generate P, P, SV, and SV. SV, all the possibilities. Okay, it's too boring. I hope you know what you should or could do. Write the potentials, write displacements, write strains, write stresses, and apply the boundary conditions, and you could have a sort of a scattering matrix. Some good news. Better for lazy people. If you have a fluid interface, solid fluid, half of the problem is gone. Why? Well, for example, in the fluid part, we can have only P waves. That's important, because now you can imagine that, and we're going to explore this afternoon, that if you have an S waves that is propagating to the mantle, arriving at the core mantle boundary is looking there, say, oh, it's a fluid. I cannot propagate there. So part of the energy will be reflected, S, but part of it, a tiny part, can become, from an SV, a P. So it will be a P wave that actually was an S wave in a solid, but now has become a P. And that was important because it has been used to discover the core mantle boundary. And later, the interface between the outer core and the inner core, because the inner core is solid. Now, if we have a P, it can generate an S that is going to be trapped there, but part of the energy can be transmitted as a P coming outside, and that will become an S. So you can imagine that there is a huge, a tremendous mass of phases that are containing informations. Not only in terms of arrival times and direction, but also in terms of amplitudes. These are the basic tools for body wave tomography. And we will see it this afternoon. What we're going to do now is a sort of a summary of what we could do, but we will do it just in part. And we will start what will continue this afternoon as a very short, tiny course on body wave tomography. First, let's make a recap. These pictures are coming from your textbook. And are showing some examples of possible ray maps. Remember that rays are just telling you the direction of moving of the wavefronts. Okay? They are useful because they are telling us the direction of K. But remember that physics is in the wavefronts that are traveling with alpha or beta. So, okay, what do we have here? Some sketches of possibilities. This is a sort of a model of the ocean crust interface. It's a very good model if you want to work for some applied geophysics problem. For example, that you have some artificial source that is illuminating with P waves the fluid. What's going to happen here? Well, you can imagine that the wavefronts are going to be propagating to water, into the ocean, just as P waves. What about the velocity? Well, it's 1.5 and no S. What can happen at the surface? Well, now we can have P transmitted and S transmitted as V. Okay? What about the directions? Well, it will depend on the values. These are faster than those, so the rays will try to turn. There will be critical angles. Yes, we have two. There is a typo here. This dashing here is not for reflected, but it is for transmitted, of course. There are no reflected S waves. Okay? Okay, now you can imagine that you can use this map here. Let's imagine to collect data here and to use this map to deduce these velocities, given 1.5, for example. What if you have a source in the Earth part? Well, now you can have P and S that are going to be emanated, radiated. They can be reflected. SV can reflect P, SH can reflect just SH, and here we have just P's. What's next? Well, we can imagine now a cross-mantle interface, as we have seen before. And now you see the values, 3.9, 4.6. It was the case that we considered before. What about P's? Okay, and now you can produce thousands of maps like this. What we have done as a summary is just to consider interfaces of discontinuity, heterogeneity, better, starting from the free surface, and then we can imagine to add others and others. Fluid, solid, solid, solid. We can write the equations, guess the solutions, and apply the boundary condition, studying reflection and transmission coefficients. Both coefficients contain the information about trajectories and amplitudes. Okay? But actually, from now on, these are different sketches, what we're going to do is something different, maybe simpler. Because actually, what we're going to call body wave tomography is to use the arrival of the different phases, P, SB, SH, and all the possible reflections and transmissions, but just using arrival times. And what we can do is to start a sort of a tomography problem that maybe you're going to explore better in the second term, maybe you're going to work on this in your future, but we are going to take just the very first and simple steps. Okay, forget about this. We will discuss this before lunch break. This is the simplest model that we can consider. It's really simple. Why? It's flat. It has a free surface. Good. It's the Earth. We're sitting on it. Then we have a layer. And then we have an outer space. Is it good, this model here? Well, yes. For example, on short space scales, it's very good to study sedimentary basins over bedrock. Nice. It's good to go to a little bit broader scale to do some geophysical, how to say, exploration. It's good to study the crust over the mantle. Please do remember, it's not good to study the Earth in a spherical system. It's not spherical. Okay. Now, this is the simplest and very solvable tomographic problem. Data. Well, we can imagine to put sources that we know in some positions, like a hammer, and to consider a set of receivers. And we know their positions. So we cause some waves, and we study the arrival times at the different position of the receivers. This problem is solvable. Good news. This problem is not realistic. Bad news. But we are going to solve it. So the problem now is to study the arrival times in a very simple configuration. Free surface, a layer, hard space. Data, arrival times, unknowns. Alpha 1 or beta 1, alpha 2 and beta 2. And the thickness of the layer. So if we are considering just P waves, 3 unknowns. If you want to consider just S waves, 3 unknowns. Okay? Which data can we use? The idea is developed in the next slides. Which kind of waves or phases are you going to weight? Let's imagine that you have to perform this experiment. So use a hammer, or on this table, you put 3 accelerometers here and you record. And you want to study the velocity of this part. Let's imagine this is infinite and the thickness. Which kind of waves are you waiting for? Okay, let's separate them. Let's consider P first. Okay. Which one will arrive first?
P.
But along which trajectory?
Directly.
It will be something that is going to travel like that. What's next? Is it going to be alone? Well, if no layer, yes. All the other energy will go downstairs. Goodbye. Just a P. Well, if you want, it's a very specific configuration of this problem. No layer, thickness is 0, we have just one velocity, we measure the time, game is over. Let's imagine that there is a layer. What's going to happen then? Well, we will have a reflection. Let's imagine the wavefronts. And according to the position of the receiver, we may have this one. Second arrival. Now, there is a plot there of what is called an head wave. It's something that is going to arrive here, to be critically reflected, travel, and then, following Fermat's principle, if you want, going up again. Is it possible? We will guess. Is it possible? Yes, if we can have critical reflections. So the necessary condition is that beta 2 or alpha 2 is larger than alpha 1 and beta 1. Otherwise, all the energy will go down and no critical reflection. And we will never know alpha 2 or beta 2. Okay, this is what we are going to solve in these 10 minutes. And then we will extend this way of working to more complicated models. Now, well, so topic for this final part is the following. Let's build travel patterns. And the typical plot is this, or reversed if you want. X is the position of receivers, given that we know the position of the source, that is in 0. So we have a receiver 1, 2, 3, 4. Now, one curve is very easy here, the direct. Well, according to the position, it will be a slope, a linear slope. It will be a line with a slope that will be 1 over alpha, for example. It's direct. What about the reflected wave? Just a little bit of algebra here. Well, the time necessary for the reflected will be to make this and then 2 times by geometry. Okay? It's like an optics problem. Good. Let's write this time here in terms of the parameters that we want to know. Thickness. And then geometry will decide the angle. So the time for the reflected wave to arrive will be 2 times this. And this is h over velocity and the cosine of I. Okay, can we write the cosine of I according to the x? Yes, we can, and there it is. Now, which curve is this? Well, it's a hyperbola that is doing something like that. And the asymptote will be the direct arrival. Well, how to guess this? Let's imagine that we go very far from the source. If we go very far, the trajectory of the reflected will be more and more similar to the direct. And actually, the thickness of a layer will be nothing. So this will be the asymptotic value. Well, at the beginning, how much it is? Oh, in x equals 0, what we have to wait is the energy to go down and bounce back. So 2 times h over alpha 1. Okay, and we're done. Because from this slope here, we get alpha 1. From this one, we get h. What about the R space now? Well, if the R space is slower than the layer, the energy will go down. Let's use Snell's law. you can understand that all the rays here will go down. They will try to go deeper and deeper. But if this is faster, we know, thanks to Snell's law, that sooner or later we will have a critical. Good. So maybe for this one there is a critical angle, and the critical angle depends only on the ratio between the two velocities. Please remember Snell's law. Okay, let's play with some geometry here. What about the possible arrival time of a refracted one, or critically refracted? Well, it has to be 2 times this. And how much is this? 2 times h over alpha 1, because it's going with the speed of alpha 1, h over cosine of IC. It has to be the critical angle. That's a specific angle. Plus this distance here that, using Fermat's principle, is going to travel with alpha 2. Okay, let's write this quantity here in terms of x, because we want all the curves to be put on x and t. That's easy. And now again, it's appearing this. Now we're going to use the condition of the critical angle. That is the most important one. Well, by definition, the critical angle will be the angle for which the refracted angle will be 90. It's by definition. So, critical angle will be the one for which this is 1. Critical angle is nothing else than the inverse of the sine of this ratio. If alpha 2 is less than alpha 1, there is no critical angle. Okay? Good. Now we can rewrite the arrival time of the refracted angle in this way here. We have just used Snell's law. Final step. 1 over alpha 2, by definition, is this. Let's call it P. Well, that's the P that we have used before. And now we can call it the ray parameter. It's a number. P has to be 1 over alpha 2 at the critical angle. No way out. What about the cosine of IC? Well, it will be 1 minus, oh, that's the old eta. Thus, we can write this expression here in this way here. What are the variables here? Not P. P is 1 over alpha 2. What about this? Well, P is given, alpha 1 is given. These are numbers. Actually, the third line, the third curve, is a line with a slope that is P, that is 1 over alpha 2. Where it is going? Well, it's starting when the critical angle is, and then it has a slope that is larger because it's 1 over alpha 2. And now we can measure the third parameter. And what is surprising is that after a distance this will be the first arrivals. Why? Because they are traveling downstairs at a faster speed. To sum up, what we can draw now are the travel times of this system here. And there you go. Given these travel times, in principle, you can get all the parameters that you want. Alpha 1, alpha 2, the thickness. And this is a sort of a plot of what you can imagine to occur here. Wait a second, because I prepared, and maybe we will, let's say, stop at this point here with some animation before an important slide that is coming. What's happening here? Why? Okay. We will continue this part later, but let me first see if this is working. But I have some, oh, it's not working. But I have some animation that I have already downloaded on my Mac. And the ROM is not working, so let me try ICTP secure. Oh God. The animation that I'm going to show to you is maybe the most important one about seismic waves. Uh-oh. Let's see. Otherwise I will try later. No, they're not here. Maybe they are in seismology. My God. Wait a second. Yeah, maybe I saved some of them here. The most important one is this one. I hope it's going to work. Okay. Why I love it? Because it's showing rays and wavefronts. Now, that's the top, that's the bottom of a layer, that's the hull space. What you're going to see now are some directions. Look at the wavefronts. Remember, from the source, wavefronts are going in all the directions. So you may imagine to have a set of rays at different angles. The direct will have an angle 0, okay? Or 90, depends. Then lower, 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 vertical. They're going in all the direction. These are the wavefronts. Let's give a look. Reflections. Let me stop it. Too late. Let me show it to you again. Now, in some time, the direct you see is traveling here. Okay? You have to imagine to be, here there is one receiver, for example. Okay? The direct is going there. It's going with a velocity that is exactly the velocity of a layer. Okay? Then we have other parts of the wavefront that are traveling in different directions. This will become the reflected, this will become the critically refracted. But now, look at the reflections. I will try to do it step by step. Some reflections occur now. You see? And they will go up. Come on. Now at this time here, the reflection from downstairs is going up. So it's this point here. X equals 0. All the other reflections are traveling. And they will be reflected other times. Let's see if I can do something like that. It's not working. Okay. Look, reflection. It's not moving anymore. So I have to play it. Now give a look to this one. That one is a little bit different than the other ones. Okay, let's let it run until the end. Look at the, sorry for the word, mess of waves that we can have just considering one wave field, pure S, into this very simple system. Now, thinking in terms of rays, It's simplifying life. But remember that, for example, this line here is nothing else than the ray that is pointing to the direction of the reflection that was arriving at that receiver. This line here is just telling us that there was the direct that was arriving there. And then this one was already arrived. Let's see if I can go back now. No. Huh. Let's see if I release it. Look at this one. That's arriving first. It's small, but that has as information the velocity of the lower layer, of the interface between the layer and the Hall space. Why? Because its expression is this one. And the slope is 1 over alpha 2. Now, where it's going to start? It depends on the ratio between alpha 1 and alpha 2, or beta 1 and beta 2. Why? Because it corresponds to the critical angle. So it cannot appear before than this. You need a distance. And the distance, that is called critical distance, will be dependent upon the ratio between the velocities. If the lower velocity is lower than the layer one, there is no, this line is not existing. But if beta 2 or alpha 2 are larger than beta 1 and alpha 1, then this can exist. And the slope will be 1 over the velocity of the Hall space. Then there is this point here at which the direct and the critically refracted will arrive together. But from that time on, this will be the first arrival. Now let's give a look again to maybe to this one that is showing just head waves. In this animation here, that is similar to the other one, there is just one ray. And it is the one related to the critical reflection. So look at the wavefronts, some parameters, in this case P waves, 8, 12, 30 is the thickness. Those parameters will decide the travel times. For the direct, for the geometry of the reflected that will resemble this thickness, and the arrival of the critical reflected that will resemble this ratio. Let's give it a look. You see, the critically reflected will correspond to the angle, exactly to the angle of the incidence of a critical angle. It's just one part of a wavefront. That's why the amplitude is tiny. Then it's going to go there as a flat wave, as a plane wave, and you will see it there. Let's see it again. Starting. Where it is starting depends on the ratio between the velocities, because that is defining the critical angle. Look, now the first reflection has bounced back, so thickness. Now that wave can radiate. You see all these lines here, and the wavefront is a line going that direction. That's a typical interface wave. And it is called head wave because after a given distance, it is the first arrival. Also, the amplitude is tiny. Now it is. Let's give a look to the final look, then we will start again at 2. Let's give a look to the amplitudes. Since the critically reflected is just a portion of a wavefront, its amplitude will be tiny. And the reflection coefficient actually is not very large. Most of the energy is on the interface. It will be the red. Now it's arriving together, you see, with the direct. And later, the reflection is coming. Okay, from this very simple model that we're going to explore a little bit in the afternoon, you can play with many models for applied geophysics, for example. You can do reflection geophysics using the refraction ones. You can use also earthquakes, but we have a problem because we don't know exactly where the source is. We cannot control that one. But if you go to broader scales, you need energetic earthquakes. That's why when we move from this model to a global model, we need seismology. And this is what we're going to finally discuss this afternoon. Okay, so to sum up, we discussed what's happening at interfaces, free surface, other discontinuities. We could solve the full problem in terms of directions and amplitudes, but usually the most important research, not important, but the most quantity of research in tomography is made just with arrival times of the different phases, most. Okay, this was one of the most tough lectures of the course. I know it was heavy for algebra, but actually the physics are not that important. Remember, boundary conditions are deciding the solutions of the dynamics. Free surface interfaces. Okay? So let's start again this afternoon. I hope that the network is going to work again for myself. By the way, in that link, there are many animations like that. I've shown to you just two, and we are going to see others this afternoon that are related to flat geometry. Okay, let's see again at 2, right? Okay.